Every time you ask ChatGPT to write an email or, generate a funny image, you're actually contributing to a massive energy problem. And it's a problem that's pushing the smartest minds in tech toward a truly radical solution. Welcome to This Explainer. Today, we're tackling a concept that honestly sounds straight out of a science fiction movie, but it is rapidly becoming a very serious engineering objective. We're asking the question, can we actually run data centers in space? Look, the fundamental thesis here is simple but profound. Building super intelligent AI is at its core an energy problem. We are literally running out of power on Earth, and that harsh reality is forcing us toward a genuine moonshot solution. Okay, let's dive into this. Here is our roadmap. We're going to cover AI's Earth power bottleneck, then move to the solar space solution. After that, we'll look at beating heat and hardware limits, surviving deadly space radiation, mastering complex fleet control, and finally, testing the moonshot timeline. All right, part 1, AI's Earth power bottleneck. Before we can even try to justify launching billions of dollars of incredibly delicate hardware up into the stars, we really need to understand the massive stakes right here on Earth. Like, why are we even having this conversation? Well, it all comes down to the staggering, almost unbelievable energy requirements of artificial intelligence. By the year 2030, U.S. data centers are projected to consume a mind-blowing 790 terawatt-hours of power. That is a 4 times increase from where we are sitting right now, in just a few short years. And it's being driven almost entirely by the insatiable, energy-dense workloads required to train and serve these new AI models.
This concentrated compute is just rapidly swallowing our electrical grid. Think about this. Right now, data centers consume about 5% of total U.S. electricity. But by 2030, that slice balloons up to 17%. And here's the kicker. You have to remember that concentrated compute requires a tremendous amount of cooling. Just keeping these machines from physically melting down adds an extra 40% to a data center's power requirements.
Let's ground those abstract percentages in reality for a second. Building just one typical new AI data center requires the power equivalent of an entirely new city. We're talking anywhere from 80,000 to 800,000 homes. Our physical construction of power utilities simply can't build fast enough to outpace our need to harness energy for artificial general intelligence. It's just not happening. Which brings us to part 2, the solar space solution. So if Earth's grid is totally bottlenecked, where do we go? Well, Elon Musk actually framed this reality perfectly. He said the only place you can really scale is space. Once you start thinking in terms of what percentage of the sun's power you are harnessing, you realize you have to go to space. And he's right. This isn't just some sci-fi fantasy. It's a mathematical necessity for scale. If AI development requires exponential power, we literally have to look toward a source that can provide exponential energy. Up in space, the core role of solar energy totally transforms. It goes from being a supplementary terrestrial power source to an absolute uninterrupted baseline. Generating power in a vacuum is just drastically more efficient. Down here on Earth, solar energy is plagued by the day and night cycle, weather, and the need for massive, incredibly expensive battery infrastructures. But in space, you get 24/7 continuous solar exposure. There's zero atmosphere to block the rays, you don't need heavy protective casings to guard against weather, and perhaps most importantly, you completely bypass the slow terrestrial regulatory gridlock of trying to make deals with local utility providers. Moving on to part 3, beating heat and hardware limits. Now, of course, space is notoriously hostile, and here is the very first major engineering mini-boss we have to face: heat dissipation. On Earth, we use fans to push air or pumps to push liquid to carry heat away from our servers. But in the vacuum of space, convection just doesn't exist. There's no air or water to carry the heat away. So you have to rely entirely on radiative cooling. This means the intense heat generated by clustered GPUs has to be physically transferred to enormous metal plates so it can slowly radiate off as infrared light. And honestly, it's highly inefficient. The sheer surface area required to do this effectively for AI workloads presents an unprecedented thermodynamic puzzle. We basically have to completely rethink thermodynamics just to keep these satellites from cooking themselves from the inside out. Compounding that heat issue is the structural reality of what we call a no-touch environment. Imagine not being able to call IT to restart your router, except your router is orbiting Earth at 17,000 miles per hour. You absolutely cannot send a technician to orbit to swap out a burnt-out GPU. This requires us to develop chips designed to run at significantly higher base temperatures. It also demands massive redundant hardware provisioning and highly fault-tolerant networking software. If a node breaks up there, the system has to instantly self-heal and route around the damage automatically. If it doesn't, that entire multi-billion-dollar cluster becomes nothing more than very, very expensive space junk. Part 4. Surviving deadly space radiation. So if the heat doesn't get you, the invisible environment just might. Let's shift our focus to a threat that Earth's magnetic field normally protects our delicate hardware from: space radiation. To really understand this, Google Research recently ran a literal stress test. They wanted to know exactly what happens to our most advanced AI hardware when exposed to deep space conditions. So what did they do? They blasted their tensor processing units, their TPUs, with a proton beam. And the results? Yeah, they were alarming. At a cumulative dose of just 2K rad, which is roughly 3 times the expected dose of a typical 5-year space mission, the high bandwidth memory starts suffering from random bit flips, uncorrectable errors, and silent data corruption. Now, massive language models with trillions of parameters, they might actually be resilient enough to survive a random bit flip here or there, but much of a data center's core infrastructure code relies on traditional heuristic logic. The logic running the satellite's core routing software simply cannot afford a single mistake. A silent data corruption there could totally sever the satellite's connection, permanently blinding it from the rest of the fleet and causing a catastrophic silent system failure.
All right, part 5, mastering complex fleet control. Speaking of the fleet, making these floating servers talk to each other and to the ground at blistering speeds is absolutely critical. I mean, the entire point of AI is fast inference, right? For a good user experience, this loop has to be flawless. A user on Earth prompts the AI, the signal beams up to the orbital cluster, the compute processes it instantly, and the results beam right back down. These orbital clusters must deliver the exact same low-latency speeds as a server sitting in a heavily air-conditioned building right down the street from you.
Now, what's really interesting here is how we achieve those instantaneous speeds. Orbital clusters have to communicate at tens of terabits per second, basically replicating a physical fiber optic cable using lasers in the vacuum of space. But because lasers and signals naturally degrade over distance, these satellites cannot be spread out over miles and miles like standard communication or GPS networks. Instead, they have to fly in a super tight formation. We're talking uncomfortably close, literally just hundreds of meters from one another. And flying in a tight formation like that introduces an absolute nightmare of orbital dynamics. You've got to overcome atmospheric drag and continuously adjust for the Earth's non-spherical gravitational pull. If one satellite drifts by even a tiny fraction of a degree, that high-speed laser connection completely severs, and the AI halts. Done. On top of that, the entire cluster has to follow a highly specific path just to maintain direct sunlight exposure for power. This requires constant, incredibly precise automated station-keeping maneuvers just to keep the cluster perfectly intact and operational. And finally, Part 6, testing the moonshot timeline. So, we've covered the incredible challenges. But when does this actually become a reality? Right now, launching payloads is still pretty expensive. It's sitting around $3,600 per kilogram, and that's even with reusable rockets like SpaceX's Falcon 9. But the learning rate is accelerating super fast. In fact, Google is actively planning to launch a small-scale trial in 2027. And their specific goals aren't just about sticking a computer in space. They want to rigorously validate ultra-fast satellite-to-satellite optical links and stress-test automated ground communications under real orbital conditions. Based on Google's own simulations, by the mid-2030s, launch costs could plummet to just $200 per kilogram. At that price point, the economics of running a data center in space become fiercely competitive with building one right here on Earth. We usually think of space exploration as this noble quest driven purely by human curiosity. But as the sheer energy demands of superintelligent AI outgrow the physical limits of our home planet, we have to ask, will humanity's quest for artificial intelligence be the very thing that practically forces us to become an interplanetary species? It is an absolutely fascinating and profound reality to ponder. Thank you so much for joining me for this explainer, and keep learning.